Hello Legacy Sabers, March here. So today I'm going to show you one example of simplifying or graphing rational functions. This is day 3. This is the more harder versions. It's not difficult, but we just need to know how to do a little bit extra. So I'm looking at number 5. It's from the worksheet from today. So first thing, remember, simplify stands for expand or like factor. So I got x cubed over x plus 1, x minus 1. Okay, wholes means if stuff cancels off. Notice nothing is canceling off right now, so there is no wholes. However, I do have a root, and it's an x cubed, so that would be a 0, right? Because if x cubed equals 0, I would get 0, 0. So I'm going to put that dot in on my graph here. Asymptotes, it looks like I have 2 of them. One located at -1, one located at 1. So it looks like we have a 3-zone problem here. Okay. Tangency. Now notice, guys, you're probably saying, well, there's duplicates in the numerator, but it has to be even number of duplicates. So just because this is x cubed, that's not even number, that's odd number. So we have no tangency, and we also don't have any togetherness either because there's no duplicates in the denominator. Okay, end behavior. Let's see if we can find some end behavior. I am an x cubed over an x squared. Well, that to me means we have top heavy. Okay, so that means we have to long divide, so I'm going to divide x cubed by x squared minus 1. Something times x squared needs to give me x cubed. Well, that's x, right? So x times x squared is x cubed. X times -1 is -x. Change my signs. I just get a remainder of x. Notice, guys, can't multiply anything by x squared to get you x. So your slant asymptote is located at y equals x. So I'm going to draw that in here. Now notice, guys, we do have a root located on that asymptote, so one assumes crosses is going to give us an actual value this time. So let's set our asymptote of x over 1 equal to our simplified version. I'm going to get x cubed equals, well, this is technically x squared minus 1, so x cubed minus x, technically, if I multiply that. X cubes are going to cancel out because I subtract, so I'll get 0 equals -x, or x equals 0, so that tells me I'm going to cross at x equals 0, which in case I found I did. So that tells me I am going to have to go through this dot somehow. It's not going to be a parabola in the middle there. Now let's find our y-intercept. So 0 over 1 times -1. That would be 0, 0. So all I have is a single dot and 3 lines. Notice, guys, I really don't know what's going on, right? I don't know if it's going to go up this way, down that way, or is it going to be flip-flopped. So sometimes, if you don't have much more about the graph and you need a little bit more of information, just like this, what I like to do is pick a dot, pick a point, pick an x value, find a y value. Honestly, you can find a graph that way. I'm going to plug in 2 because I'll find out, is it below here or is it above here, and then by togetherness and all that I can start figuring out the rest. So let's plug in a 2. So if I plug 2 in, I'll get 2 cubed over 2 plus 1, 2 minus 1. 2 cubed. 2 times 2 is 4, times 2 is 8. 3 times 1 below that. So 8 over 3 would be my ordered pair, 2, 8/3. So that would be 2 2/3. So right about here. So notice, guys, I can't cross the slant except for right here, so I am going to go forever this way. I think I should change color here. Oop. Erase that quick. Change color for you guys so you can see it. So I got 2 2/3 right there. So I'm going to go like this. Go up at that asymptote right there. Not much of a point there, should be more curved, but you get the idea. We are not together at y equals 1 or x equals 1, so I know that this place has to go downwards, go through that x equals 0, go up, really quick cubic polynomial in there, and then I know that my graph has to do something like that as well. So if I look at my domain here, I can't have -1 and I can't have 1, so I'm going to put both of those on my thing. And then if I look at range, notice, guys, I'm going forever down and forever up. So my range is -infinity to infinity. And that's the end of this video. See you later, Sabers.